We've all done it. You open a little door, punch in a number, and 60 seconds later, yesterday's cold pizza is steaming hot. It feels almost magical. But how exactly does a cold metal box force a water droplet to flash right into steam without using fire or red-hot metal coils? That box on your kitchen counter is a highly precise, micro-engineered factory. While a traditional oven wraps your food in hot air to slowly push heat from the outside in, this system works in reverse, forcing the food to generate its own internal heat. Let's pull this machine apart. Behind the casing, 13 distinct components work as a linear assembly line. Energy flows from the bottom up to the cooking chamber. The journey begins at the electronic control board, where your input triggers a routing sequence within this circuitry. The control board's sole purpose is to translate your desired cooking time into a precisely timed electrical routing command, directing power to the heavy machinery next door. That power travels straight from the control board over to this heavy, boxy component wrapped in copper wire, the high-voltage transformer. Standard household wall electricity provides 120 volts, fine for a toaster, but far too weak to generate the specific type of energy required here. The transformer acts as an electrical power lifter. It takes the small, low-voltage wave entering the primary coils and uses electromagnetic induction to multiply that voltage into a massive high-amplitude spike. Creating this dangerous stepped-up voltage is the absolute prerequisite for fueling the system's primary energy converter. That supercharged electricity now slams into the primary energy converter, the magnetron unit with its stacked cooling fins. This vacuum tube converts the raw electrical current into invisible electromagnetic radiation, changing the form of the incoming energy. This chart shows the full electromagnetic spectrum. Notice where the magnetron's output lands. It produces waves that sit right between radio waves and infrared light. We call this specific frequency band microwaves. Because these microwaves behave like beams of light, they require a specific path. They are directed out of the magnetron and through this hollow waveguide channel, which leads straight into the main cooking cavity. In just a fraction of a second, the machine has successfully transmuted raw electricity into a controlled beam of invisible energy. Once those waves blast into the internal stainless steel cooking cavity, they don't just sit there. The thick metal walls act like mirrors, bouncing the energy rapidly around the enclosed space. These waves pass harmlessly through air, glass, and most ceramics. However, they are highly attracted to the water molecules found in almost all food. This is dielectric heating, a process where a high-frequency electromagnetic field forces polar molecules to rapidly rotate. A water molecule naturally has positive and negative ends. When a microwave hits it, the wave's changing electrical field forces the molecule to flip back and forth billions of a second. As millions of water molecules rotate, they rub against neighbors, creating intense physical friction and kinetic energy, perceived as heat. The result is a unique thermal environment. Instead of applying heat externally, the machine forces the food to cook itself through its own molecular friction. But this invisible energy has a flaw. As the waves bounce and cross over each other, they create standing waves, zones of intense energy and dead spots of no energy. This is why soup can be boiling on the edges while remaining frozen in the center. To solve this, a turntable motor beneath the glass plate constantly rotates food through the energy field. To achieve textures radiation cannot produce, premium models include a convection heating element and fan assembly, blowing hot air over the food. Combining internal molecular friction with external convection guarantees even internal temperatures and a crispy outer texture. All this energy creation generates waste heat. The cooling fan assembly pulls fresh air across the magnetron's fins to prevent internal melting. For human safety, the machine must also protect anyone standing right in front of the glass door. This right here is a Faraday cage, a conductive enclosure that blocks electromagnetic fields. Because the physical wavelength of a microwave is relatively wide, The holes in the metal mesh act like a solid wall to the radiation, while still allowing much smaller light waves to pass through. Finally, the outer stainless steel casing is lowered into place, sealing the moving parts, high voltage, and radiation safely inside. The humble microwave isn't a mere hotbox. It is a perfectly orchestrated symphony of extreme physics and high voltage electronics sitting safely on your kitchen counter.